so we get started. We are very pleased to have distinguished speaker, Professor Josef Kittler from the University of Surrey in England. He's one of the most famous researchers in pattern recognition. He received the KSQ award, the most prestigious award you can get. And he got his PhD from Cambridge University and has been at the University of Surrey since '86. Established center, vision, speech and signal processing, big center, more than 100 researchers participating in the center. He has written very popular book on pattern recognition, fellow of societies, and he has also startup and so on. So we are very pleased to have Josef here.
Thank you very much for the introduction. It's a pleasure to be here at the University of Florida. It's the second time I'm visiting this particular university, and I've been in Florida on other occasions and in other parts of Florida before. So I'm going to talk about anomaly detection. Not quite sure how it will work. But I will be neglecting part of the audience. It is so wide, and I will have to work out the best way of doing it. Interestingly, also, the room 101 has a very strange connotation in English culture. Is it the same in the US? There is a guest show in UK, and as part of the activity in the show, there are people from the audience who come to tell a story, and they sit in a chair, and if the audience doesn't like the story, well, it's not the audience, but the people who are being invited to the show, the guests, if they don't like it, then they press a lever and the speaker disappears, the chair overturns. So I hope you are not wired, this is the way here. Okay, so I will be talking about anomaly detection in machine perception, and it's a topic which I've been always interested in, but perhaps without realizing in the past. But over the last 5 years or so, maybe even more now, I had special interest in this topic for two reasons. First of all, I was one of the reviewers of a big European project which was focusing on nothing else but anomaly detection. So that had, something like 5 million euro funding, similar to about $6 million, and over 4 years. And so we were monitoring the progress of the project. So that made me interested in the problem of anomaly detection. And at the same time, in my lab, we had a project which also involved anomaly detection. So these two things sort of work in tandem, and I got interested in the problem and focused on it for during the last 2 years. So I will actually introduce it as, I think probably everybody is familiar with anomaly detection, what it means, but I will comment on the standard formulation of the problem of anomaly detection, and we'll see that there are some sort of deficiencies, and we will come up with a proposal for more complete way of looking at the problem, and we'll then see a few applications of this more complete formulation of the problem, or maybe identification of what components an anomaly system should contain, and I will illustrate some of the ideas on a few applications, but don't expect solutions. It's more, I think the take-home message will be, there is more to anomaly detection than simply outlier detection. And one has to, there are many challenges, many issues, so anybody who is starting on a PhD now is hopefully will be perhaps of interest that might be, may provide an area of your research focus. So, what is anomaly? Well, I think everybody knows what anomaly is. It's a very important concept to all biological systems, not only to human beings, but also to animals, because very often it's a question of survival if you detect something anomalous, something that some data that you sense which does not fit your current model. So normally we operate by building models for the sensory data that we receive, and if there is something that cannot be explained by the existing models, then we would consider it as anomalous, and that may be very important from survival point of view, but it's obviously very important to humans because we have many synonyms for the word anomaly. And here are just, there are many nuances to it. So it's like Eskimos, they have about 25 different terms for snow, whereas people in the south, the warm climate, in just one term. And so the synonyms for anomaly that do exist don't have exactly the same meaning. Okay, so sometimes we call about detection of rare events, something very that happens very seldom, not very often, and so it's sort of associated with anomaly, something that does not happen normally. Irregularity, you expect some sort of regular pattern, and if that pattern is broken, then the observation is irregular, and so again it's anomaly. Incongruence, there is some sort of disagreement between sources of information, and again, if there is a disagreement, it may suggest anomaly. Abnormality, unexpected event, something that would not normally happen, and it would be considered as anomaly. Novelty, when something new experience is made, it's effectively anomaly with respect to the models that we have, the models of the world that we have at the moment. Innovation, when again it's anomalous, but it's a change of state. Suddenly you start observing something different from what you had before, what you saw before, and but then the observations of the world remains in that new state, and so would refer to it as innovation rather than just anomaly. So you can see that all these different terms, which effectively mean something unusual, are represent some sort of nuance of anomaly. They all correspond to anomaly, but it's a nuance of anomaly, and you cannot necessarily all interpret them simply as an outlier, which is a standard way of formulating anomaly detection problem, and I will come to that more detail in the next slide. But what are the various applications? Well, I think probably the most common one is surveillance, or application where you are monitoring some sort of site, looking for something unusual. So you would model normal behavior, and whenever something unusual happens, for instance, some disturbance in a railway station, underground, airport, then you would like to detect it because it may indicate that there is you should pay attention and see whether you need to take some measures, respond to it in some way. Novel object detection. Very often, especially in pattern recognition, machine learning, we are interested in identifying situations when we are suddenly observing a novel object, and so that can be considered as anomaly with respect to the existing models that you have. You may be interested in detecting anomaly in communication networks, as there has been certainly lately. There has been a lot of cybercrime and a lot of interest in that area. Medical diagnostics. When you are trying to find out what's wrong with people, you are looking for anomalous symptoms, manifestation of the problem that patient may have. So you will be looking for anomalous manifestation of some disease in medical data. Video segmentation, okay, again, can be considered as a problem of anomaly detection, where you see content changes, video content changes, and you may be interested in formulating as anomaly detection. So what is the standard way of doing it? Well, we are used to modeling normality, what is normal, and this is, so we will have some sort of measures, some statistics, some information that we would collect and find out what is the statistical distribution of this information for normal scenarios. And then, if you make an observation, okay, somewhere here, so this was our statistical distribution of the measure that we work with, if we observe, make an observation somewhere there, then obviously this observation is not consistent with our statistical distribution. We would say what is an outlier of the distribution, and it represents some anomalous situation. So this is a standard way of defining, formulating the problem of anomaly in a mathematical way as an outlier of a distribution. And there is a huge amount of literature on the topic, probably hundreds of thousands of papers, and some of them date back a long way. So earliest work detected, I think, or identified was in the 19th century. People were interested in scientific area, in biology, they were collecting samples and modeling what is normal, etc. So working with Gaussian distributions, normal distributions was very popular at the time, and also the notion of anomaly, what is deviating from the distribution has been defined at that point, and started researching it quite intensively. And there are many papers, and if anybody wants to move into that area, then it's best to start with some survey papers, and indeed it's very helpful. There are excellent surveys on anomaly detection, and we have got a few examples of survey papers here. But what is inadequate with the standard formulation of anomaly as an outlier for the distribution? We have a number of problems and I'm referring specifically to machine perception. I believe quite a few of you are working in this area in one way or another. In machine perception systems, we have many models, we have many classes of objects, we have objects which are configured in the world in various ways, and so they have rather complex systems, and detecting anomaly is quite difficult, because what may be anomalous with respect to one model may be perfectly normal with respect to another model, and if we have hundreds of models, then the problem becomes difficult just in that sense. We often work with discriminative classifiers in machine perception because discriminative classifiers are computationally more efficient. They are also they usually have better performance than generative classifiers. But the problem with using discriminative classifiers is that you don't have a notion of whether you are dealing with outlier, some unusual measurement or not. Because once you are on one side of the boundary, then the classifier tells you, well, this is class X, and you can be miles away based on an observation which you have never seen in training data, and the classifier will still happily respond with quite confident answer. So we have a problem that very often these discriminative classifiers are not amenable as a source of information that can be used for gauging anomaly. We have very often problem with ambiguity of interpretation. Sometimes the measurements we use are ambiguous in some part of the observation space, and that also creates difficulties when one tries to identify anomalous situations. We have in machine perception, we have knowledge organized in hierarchical levels, which allows us to do contextual reasoning and perform better, make recognition with greater accuracy than just using measurement information relating to a single object. But this creates also one hand opportunity, but on the other hand, you have multiple classifiers which are voicing opinion about some data, and you may have sort of incongruent information arising from these opinions. Hierarchical representation already mentioned. I mean, you can have contextual reasoning without hierarchical representation. But on top of that, very often, especially in computer vision, you are representing the world and the information captured by a camera in terms of a hierarchy of motions. We have an issue of data quality, which conventional definition of anomaly doesn't take it into account. And very often we inflict anomaly problem on ourselves by trying to make our system very efficient. So very often, if you imagine that your complex machine perception system deals with more and more classes, then to make decisions efficiently, you very often organize the classes, you ignore the ones which are unlikely to happen and deal with them as a secondary phenomenon, but very often that means that number of hypotheses will not exist in the first list of hypotheses that the system will be considering. And so if you actually make an observation which corresponds to some of the pruned out hypotheses, then you will have it will be detected as anomaly. So we can see that all these problems are not really handled by the classical notion of anomaly detection, which is represented here. So we have, the classical notion deals with this sort of situation. We have a sensor, we have some very simple model of the data that the sensor is collecting, and model of the world. And if we observe an outlier, then we flag that, and the action which responds to the sensor data is modified as a result of outlier detection, anomaly detection. But that sort of classical and simple approach is not really dealing with all these problems. So how can we actually incorporate, or how can we do things more sensibly? this is what we have been looking at, but just a couple of more points expanding on some of the issues that I identified. So data quality. So imagine you considered an anomaly detection problem, you modeled your data, ended up with nice statistical distribution, and okay, well, then you would say, well, I will detect anomaly as an observation which is not explained by the distribution, but is usually defined in terms of confidence measure. So if my distribution can decide how much of the data probability would be will correspond to normality, very often it's sort of like 99% to 95%, and whatever level of confidence you decide on, define some sort of cutoff threshold. And if you make an observation beyond that threshold, then you would say, well, it's an anomalous situation. But suppose you have some noise on your observations, and your distribution changes from this red one into the black one, then you can see that this threshold, which you are happily using with your original distribution, will no longer work. So that's why we need to take data quality into account. Confidence in classifier output, again, we will have examples of that, but if I'm working in an area where there is a lot of ambiguity about, based on the information that I'm observing, I can measure it in some way, but I have to be careful how the system reacts to the sensory data, so that I don't make undue conclusions of anomalous situation in cases that are dealing simply with ambiguity. Incongruence. Okay, so this is an example of incongruence. So this is the famous Marguerite's painting. Okay, so if you look at the objects in the painting, on their own, they are clear, it's perfectly clear what these objects are. So if you have an object detector which can detect locomotion, you can detect fireplace, clock, etc., then the system would be very happy, but the configuration of these, it doesn't make sense. You know, you do not expect a locomotive jutting out of the fireplace. So that's basically when we are dealing with contextual information, we may have a number of objects in the scene. Each object may be nicely and correctly interpreted, but the configuration of these objects will not necessarily correspond to some sort of world realistic situation. Okay. There are also various aspects to anomaly. So when we talk about anomaly as some sort of general problem, actually there are different types of anomaly, let's say, and we can see that by looking at this picture. So I could test your ability to detect anomalous objects. So how many anomalies can you see? So obviously this one everybody can see, but any more?
Yeah, that's the way.
Yeah, very good. So this feature has different angle there. Any more? Yeah, very good. You know that?
Yeah, the purple stuff.
Yeah, the bear is a little bit lifted. Okay, anyway, so you can see all these here. So very good. So you can see that all these anomalies are slightly different. In one case, it was just a shift. In another case, it was some sort of more complex geometric transformation. In another case, it was an insertion of an object. Anyway, since you are quite good at it now, then about in this case? How many?
Color of stars. Maybe the projector.
Any other suggestion?
Color of plants.
Yeah, that's what was already suggested. Well, there's
The
another
ribbon
way.
around the neck of their.
Just cut off.
Here.
I think the stuff right above the wing, this particles will stick.
Actually, everything is anomalous. And why? Because in this image, because of noise products, I mean just quantization noise, every pixel is slightly different from the pixel in this image, and then you actually look for an outlier in the distribution, then it throws all the pixels out as anomalous. So you can see that the data quality has to be taken into account, and it's a very important aspect of the process. So this brings me now to a proposal what an anomalous system should take into consideration, anomaly detection system should take into consideration. So this was our original, very simple system which was detecting anomalies as outliers, and here we have a system which more corresponds or represents machine perception system, because you can see that it has two stages. It has non-contextual, low-level processing, edges or whatever, and then you have some sort of contextual processing which combines the low-level information in high-level objects, or you could have an object at this level and scene at that level. So we have two types of decision-making processes at least. You may have many more, and it doesn't have to add levels of knowledge. It can work also with modalities. You can have different modalities in biometrics. You may have a face modality and voice modality, fingerprint, and again you have multiple decision-making systems, and it's important to measure how congruent or how much they agree with the final decision. Anyway, so this is representative of many situations in a complex system, and you can see that if you really wanted to take into account the various comments that are made about classical way of detecting anomaly, then you would have to detect anomaly with a much more complex system, which has many components. So it has the standard, classical notion of outlier detection also. This is not necessarily always engaged. You would engage it perhaps only when you have some other symptom of something going wrong, like for instance your incongruence detector, which measures the discrepancy between the support for hypotheses, different hypotheses at the non-contextual level with the support for hypotheses at the contextual level. So you can have an incongruence detector. If that fires, you may then engage these outlier detectors. You need an outlier detector both for non-contextual processes but also for contextual ones. So we have that here. We have the incongruence detector. We need to measure confidence in our decisions, because that may also bear on anomaly detection, and we may be interested in detecting also model drift, when our models of normality are drifting, and you would not necessarily detect it from a single observation. And very importantly, is data quality assessment. So this is much more complex mechanism for detecting anomaly, and it's not actually a simple mechanism. Actually, the mechanism itself, these are just sources of information that are needed for anomaly detection. About how these sources are used, let's an open question. This is why I have here this reasoning box with no answers. But nevertheless, you can see that all these bits of information need to be taken into account to make a correct assessment of the data that you are dealing with and see whether there is anything anomalous. You can, it's a more complex system like that, you can have a handle on different situations. And as a matter of fact, this will allow you to assign some nuances to any anomalies detected. And so, for instance, you will be able to distinguish between situations where your low-level models work well, but your world model, which looks at configurations of low-level primitives or single objects, you are not able to interpret them. Like, for instance, in this Magritte painting, okay, you had low-level objects detectors working well, but the configuration of these objects doesn't make sense, then that will be detected as anomaly. Equally, you can have a high-level model working correctly, but low-level models not functioning. And to give you an example, for instance, in speech recognition, you have phonemes, and in some languages the phonemes are different. In many European languages the phonemes are similar, but you may have a language in which actually phonemes are different, so your phoneme detector will no longer work reliably. Also, if it is different language, that also the high level linking of phonemes into speech segments, into words, will not function correctly. But you could have, for instance, low-level decision-making system working well, phonemes detected correctly, but you cannot link them into anything meaningful. Why? Because maybe a word doesn't exist in your vocabulary. So you can start discriminating with all these mechanisms that I indicated that should be taken into account. Because you can start indicating what's going wrong during your interpretation process. Is it actually the low-level system? Is it one modality or is it another modality? Is it the model which has a sort of global view of what's going on? Is it a problem with data quality? Because if I, for instance, as we saw in the example earlier, about the speech example 2, if I have corrupted speech data, I should not be interpreting it. I will not be able to recognize the content, but I should not be interpreting it as anomaly. I should just should be able to detect that the data quality is different from the data quality I designed my machine perception system for, and make a decision accordingly. So these are some. We have been quite interested in incongruence detection because that's one of the mechanisms which are considered very important and was very important also in this anomaly detection project funded by the European Union, which is called DIRAC project. So you will find probably quite a lot of information on the internet on the project, and one of the key players in the project was Daphne Banshaw, well known in the computer vision community. But anyway, so there has been some work done in this area before. And
Chance is here, Stanford. She's at Stanford?
No, she's in Israel. I think she quite often comes on sabbatical. Normally is in Latin. So, for instance, we are interested in incongruence detection in the context of computer vision project, which was concerned with automatic annotation and storing in tennis videos. And we originally worked with using Bayesian surprise measures. So what is incongruence? You have two classifiers they are outputting probabilities for various hypotheses, and if the support for various hypotheses is different, produced by these two classifiers, then you have incongruence. For instance, one says, well, it's a ball, and another one says, no, it's some other object, then you want to, this will be incongruent observation, and you want to be able to test it, and you can suggest that there is something anomalous. You can use, for instance, Bayesian surprise measure. This is what was suggested in the computer vision literature. So it just measures this quantity, basically compares the a posteriori probabilities produced by these two classifiers, and we found that the Bayesian surprise measure has some sort of desirable property that its values are not confined to finite intervals, so it's very difficult to define thresholds on that. And anyway, so we developed a much simpler measure of surprise, which just identifies the dominant hypothesis produced, supported by the two different classifiers, and measure the differences in a posteriori probabilities for those two. But this is just assuming that your a posteriori probabilities are estimated correctly. Normally they will be subject to some estimation errors. So if you take estimation errors into account, then okay, so every probability will be corrupted by some estimation error, and if you then want to set thresholds accordingly, then you have to look at the sensitivity of these incongruence measures to estimation errors, and we have measured that for under the Gaussian, modified Gaussian error distribution. We have measured it for this moral surprise measure. You can see the Bayesian surprise can have much, the range of values can be much larger, which makes it very difficult to set sensible thresholds.
So in this you had mu taken a couple of slides before.
Yeah.
What was the mu?
U is the noise variable on your estimates of posteriori probabilities. Okay, so we are just assuming that it's normally distributed, but it's a pretty noisy Gaussian, which make sure that your estimates of probability satisfy axiomatic properties of probability.
So your data you put the Gaussian to that, and then you will know that what is right or
Okay. The incongruence measure, which measures difference between the distribution of probabilities of the hypotheses, itself has a range of values depending on the scenario, how much the probabilities differ, whether there is a switching of labels between the most dominant hypotheses supported by the classifiers, etc. So different scenarios. So even without any estimation errors, we may have a range of values that probably incongruence measure can take. And on top of that, this is sort of further aggravated by the fact that the actual probabilities will be affected by estimation errors. And so this is what we have been looking at, and we have modeled the estimation errors with Gaussian normally distributed errors, and see how it would affect the incongruence measure, and whether it would be easy to set thresholds of incongruence and say, well, this is incongruent situation, or this is congruent situation, and the classifiers agree. So, for instance, their project, they demonstrated the use of incongruence, for instance, in detecting novel type of object. So they had an experiment where they had a generic motorbike detector. Okay, and then they had specific motorbikes. So at the second level, they had classifier motorbike detectors, and So if, for instance, you had a generic motorbike detector, so either motorbike or not, once you reach the next level of the hierarchy, you may be interested which type of motorbike it is, but if it is none of the existing specialist motorbikes like cross motorbike or sport, then you want to flag it as a novelty object. And so they show that you can use this incongruence detection idea. In other words, discrepancy between the output of the generic and specific classifiers. As one example of anomaly detection, where anomaly is basically novel object. We tried that, they showed it on motorbikes, we actually tried to repeated it in motorbikes and tried to use it on other classes of objects, but turned out that if you, for instance, consider air transport against road transport, then it didn't work very well. So these are sort of image classes of the Caltech database that we work with, and you can see that you get very high confusion between objects because if you look at a bus, for instance, an aeroplane, then there is not much difference in the way they look. In many windows, some sort of a body which shell which contains the window. So it was obvious after we had done the experiment that if you want to use this idea for detection of novel objects in computer vision, you have to be very careful, and what you have to work with are visual hierarchies rather than sort of logical hierarchies or classification hierarchies of objects. When we learned that experience, we tried it on another application which was much more fitting the idea of visual hierarchy. So we classified at the first level flowers, this is the Oxford flower database, into different according to color, and then within a particular color you are able to identify subcategories in that group, and if, for instance, some category was missing, it was quite easily detected with this scheme which I described. But the problem is that there are some flowers which will not fit in with this. You may have roses of any color. Okay, so how would you actually deal with objects like that? So this idea of using it for novel object detection within a hierarchy of objects sort of half works, but it still needs some sort of proper solution to it and organization of the objects in the world so that one can take advantage of this anomaly detection mechanism that I described. But our own work was concerned with video interpretation, as I said, and in particular sports video. And so just a brief segment of video from tennis of singles, and we built a system. It took us about 8 years, which can do that quite reliably, and which means about 5% correct. Okay, so it's not perfect, but we are not using all the levels of interpretation, so we can actually award players a point depending on what happened in the scene, and it involves quite a complex system. But then we tried the tennis of doubles, and the system failed. Okay, so part of this big project that we worked on was concerned with transfer of learning and addressing the question, what can we actually do? So we have an existing vision system. How do we know that it's now dealing with a new domain, and because it's dealing with it, so you have to detect that to start with. But because it's dealing with a new domain, maybe not all aspects of the system or subsystems of the system will fail. So edge detection will still function. Many interest point detector will function. SIP operator, many aspects of the system will work, but others will not. And you need to find out which parts of the process are detecting some anomalous situation which will indicate that you need to update that, and then you are constantly how to do the update. But the first simply starts was, well, can we actually take a video of doubles and detect what's anomalous from the point of view of normality as defined for video of singles?
So what was the example of anomaly in the singles?
First of all, you have more players. And secondly, when you play doubles, and second, you are using also the tremolines, okay, so you use a wider chord. And so this is what the system actually did, and it found out that indeed if you are looking at the number of moving objects, because the notion of a player in the system is very simplistic, anything that moves. And that has the disadvantage that, for instance, when you have boys who are collecting tennis balls after the match, they are moving also. So sometimes you have 5 people, sometimes you have only 3. You can see the judges, line judges, they are people, but because they are still, very often they are considered as part of the background, but sometimes they move and they add, so you have distribution of the numbers rather than a specific number, but you can see that for singles it's different than for doubles. Anyway, so we designed the system so that anything that is inconsistent with this distribution would be detected, and we have done. You can see that we actually processed a lot of video. We have many different matches from different tournaments, and quite a lot of video data processed automatically. And turned out that in some cases, so we always trained on 2 videos of singles, then we tested on the remaining video to make sure that we don't detect anomalies and see whether we detect anomalies in doubles. And it all worked pretty well, but not in this case when we trained on Australian women singles and Japan women singles, and then the third tape, which was men singles, I think was outputting some false anomalies. And when we actually looked at it in more detail, it turned out that the Australian video had much more noise, and it was actually detecting anomalies because we were trying to detect anomalies in a material which had a data quality which was different from the data quality on which we trained for normality, and so just shows you that this one of the mechanisms that I talked about was absolutely essential. Maybe, well, I have one more application which deals with this anomaly as a detection of the tennis ball falling into the trem lines in this wide tennis court used by couples, but just again shows that we can do that. Actually, I can show you. It was interesting in a sense, let me not talk about the detail, but the problem was interesting in the sense that we have always paid very careful attention to the fact that you cannot train for anomaly. Sometimes people say, well, let's collect some data to represent anomalous situation. You can never do that. The only thing you can really learn, you can model, is normality, and this is indeed the philosophy that we follow here. and we use the same contextual interpretation model to generate incongruences between contextual reasoning about data coming from the video and non-contextual reasoning, and that allows us to identify all the anomalous situation where the game continued in spite of the fact that the low-level system said, no, this is a fault, this is ball out of play. And you can see that this is the representation of the tennis court, this is the area for singles, these are the trim lines for doubles, and this is outside the court. Okay, so this represents from the outer line infinity. And you can see that all the anomalies that we detected were actually falling nicely into the trim line. We made sure we engaged also the confidence detector, because we are analyzing the video, which is recording 3D scene and mapping it into 2D, and we are doing the interpretation in 2D. So we have problems in measuring 3D information from the 2D, and that means that we have some ambiguities along the lines defining the singles chord, okay, this line. And so all the detections, all the events, visual events which happen very close to this line were ignored. We dealt only with detections in which classifiers were confident, but you can see that the system performed well. So, just to conclude, I hope that I have persuaded you that for anomaly detection we need more complex mechanisms to solve the problem. There are quite few of them. The standard outlier formulation of anomaly detection is not appropriate, and we have tried it on a few applications. We are now doing something in biometrics, detecting new subject by this mechanism. And anyway, I believe there will be a lot of interest in this topic in the future. And we have what I talked about. We have a paper coming up with PAMI. It was accepted about 2 months ago, but it's already available from Computer Society website, but it will appear next year in the paper form. So if anybody is interested to read in more detail, you can find it there. And with that, thank you very much for your attention.
Any questions? Yeah.
I have 2 questions. So one of them is that you mentioned on some slides that you were doing some color classification of flowers.
Yeah.
So color classification itself is not an easy problem. How did you guys beat that?
I think in the Oxford database, I think it was quite uniform and coherent database. So it was not collected, not like Flickr where everybody provides their own images. So there was reasonable consistency between colors of flowers, different images. So we didn't have a big problem. We just used standard color representation.
So another question that I have was that, like, in all the systems that you were talking about, it seems that everyone, in order to take the anomaly, they try to define a set of rules and define what is a normal behavior in order to be able to detect the abnormal or anomaly. So is there any system that you can find out the normal behavior in an unsupervised way, and people try to do that?
Well, in principle, you can just model the probability distribution, and say whatever is consistent with this probability distribution effectively is normal, because I have observed it before. And this is what you could do. And in a way, this is probably the best way. If you have a complex system which has models for different classes, then probably a simple way to model what is anomalous would be to model the mixture, so actually ignore the labels and just model the mixture distribution, because then if you have an observation which is not consistent with the mixture, you will know that it will be anomalous with any of your models that you have. But but that's coming back to the notion of outlier detection. Okay, so that's just variation on the classical thing, but in more complex systems where you have multiple modalities and multiple levels of interpretation, you can do more than that.
So the mixture you're saying is of what? Like normal and abnormal?
The mixture can be anything. You know, if you have multiple classes, then the mixture will not be normal, because even if the classes are normal, which is just union of all the class conditional distribution.
And then you will be, so it's clear that your one class you model as the distribution is outlier probability of that occurring in the so, now if you have say two classes, then you say you will have a joint distribution of two classes.
Yeah, you do that way. Yeah.
And then how would you
well, then you would need basically an outlier detector.
Yeah. So you will say that this particular sample is outlier or abnormal in these two classes. It doesn't belong to two classes, but it is but you want to distinguish that it's outlier class 1 and class 2. There was another question here.
So in part of your talk, you mentioned about finding the novel objects for the case of multipliers. And it was basically comparing the outcome of a few classifiers. How do you evaluate that when your classifier doesn't recognize that object as a motorbike? So your outcome was that, okay, so this is a novel object.
Yeah.
But there is another scenario that your classifier couldn't detect it as a motorbike because it couldn't handle the intra-class variation in the motorbikes. How do you decide that this is, which case is this?
Okay, well, you can always find situations actually, even for this problem, which was considered as working very reasonably well. I think there was about 10% of cases where you could not detect the normal object. Okay, so there were situations like that. Now, when you are sometimes detecting anomaly is a single missing anomaly once can be completely disastrous. But in other situations, it's enough to find out that once or twice you detected that there was something anomalous, even if many cases we missed it. But that alone gives you an idea that you should handle that situation differently. So in some situations it will be disaster, in some situations you just miss it. Okay, so if it was, but you are saying if it was intra-class, due to intra-class variation, well, that would not necessarily stop the generic classifier to say that it's a motorbike.
In fact, if your learned model
Yeah.
is not, because none of the learned models are perfect. That's why they do not perform always well. They miss some of the objects.
Yeah.
But the outcome of your decision in this scenario is that, okay, if all my classifiers fail to detect it as a motorbike, this is a novel object. I'm saying that maybe it's a motorbike, but that's because the classifiers do not perform well.
Yeah.
How that decision is made was my question.
Yeah, I don't have answers for that, because if your top level classifier fails, then you have it. Okay, so if it, for instance, misses the motorbike, then it would not even get to that specific level, and you would miss it altogether. Equally, if something filters to the specific level and it's not a motorbike, and the way the classifiers were trained, there were some background images, and there is just set few background images to train the classifier against against set of motorbikes. But the number of images, well, different types of images that you can have. I mean, just infinite. So there will be situations where it will not work, and certainly for the airborne vehicles or air transport and road transport, it was obvious that you cannot solve the problem in this simple way. But the mechanism was useful. I mean, for some applications, this incongruent detection proved very effective.
Any other question?
Yeah, what are your thoughts about lack of data when you're training your model? Like, for example, you have surveillance in a traffic scenario. You may have hundreds of turns, left and right turns, but maybe a couple of U-turns. You might think are anomalous or outliers, but you don't have enough examples of.
That's always a problem in any application of computer vision and others of sensory modalities. That for some situations you have very little data, and it's going to be very difficult to learn what is normal. Sometimes you do it by whenever it's appropriate. I mean, that applies, for instance, even in biometrics. So very often, you can train on many people, but for one particular individual, you may have just one or two biometric samples, and you can, sort of standard practice is to use the generic model that you acquired for all the people, and then adapt it to a particular individual. But it's not always successful. That biometric systems are not 100% successful. So, the data paucity is a big problem, and the converse also is true, that the more data you have, then the better performance you will get. So there's no magic solution.
Because it's also work in the direction of trying to train models to detect rare behaviors or abnormal behaviors. If you have a few examples, only a couple of examples. It's easier to train a model for the abnormal.
Yeah, you are perfectly right, and this is what people show, for instance, in various studies on one-class classifiers. Because one-class classifiers are an extension of the outlier detection problem. And you can use standard machine learning tools like support vector machine. So basically the idea is that here I have a collection of data, and let me enclose it by some surface, and anything that lies on outside is then an outlier. And it was shown that if you are just training using the normal data, you will never get as tight and fitting boundaries as if you have just few examples of the anomaly. But then if you can have examples of anomaly, that's great. But in many situations, you don't even know what will be anomalous. So it's very difficult, to collect data, and sometimes it's impossible to collect data beforehand. You have to do some perturbation studies in power stations or whatever. Anyway, so you are perfectly right that if you have some examples, it helps. But the idea is that really in future you will have systems that will not only be designed on given data set, but in situ you will continue learning and improving performance and with human assistance. And so this is probably the way that we work more successfully in the future. At the moment, we just design the system with limited data set and then consequences.
Any other question? Okay, well, thank you very much.